Hello guys, nice to see you. How are you doing?
Good afternoon.
Hi. So how was the midterm? Was everything okay?
Yes. I have a question about our homework in lone kappa. There is one problem, electric potential from electric field, and in the comments in the discussion, they told us to find the potential at the origin minus the potential at the point, and I did exactly that. And I double checked everything, so I'm 90% sure that my answer is correct, but in lone kappa, the answer, the magnitude is the same, but the signs are opposite.
Okay.
Can you please check that problem out?
For future, to clarify how we deal with similar issues, when you believe that, after double checking, of course, that there is some issue with lone kappa problems for homeworks or midterms, you make a screenshot of the problem, also make a copy with of the problem with your answer and answer of lone kappa. Also copy some picture of your solution, which is written clearly, step-by-step solution, and then send it to me. So we will take this into account during our meetings with all other instructors, because definitely if it is indeed some issue with lone kappa, then similar issue happens with other students. So that's why we always do this kind of centralized. And then if it was a real issue, we will take this into account by correcting your grades.
Okay.
So
Thank you.
the procedure is screenshot of the problem with the lone kappa's answer, with your answer, and copy like some photo of your step-by-step solution. But should be clear so we don't waste our time trying to figure out something or also make a mistake while trying to interpret your answer. So should be written clearly, and then we will take this into consideration.
Okay, thank you. I'll send it to you later.
Sure, no problems. Okay, any more questions, ideas, complaints? Then I think we can proceed further. And I would like to maybe shortly remind you what we did last lecture. So we introduced already quite important concept of electric current, which is the rate of flow of electric current, of electric charge through the cross section of the wire, and defines as if electric current is constant, then it defines as delta Q over delta T, or if electric current is a function of time, then we just need to take derivative, and derivative at each time point will give us certain so-called instantaneous value for electric current. Also, we introduced the Ohm's law in differential form, which is current density equals to sigma times E, where sigma stands for electrical conductivity, and E is electric field. So again, I focused your attention last time on this, but I believe it's useful to remind that before that we were considering electrostatic equilibrium, and under electrostatic equilibrium condition, we do not have any electric field in the volume of the conductor, like inside conductor. So electric field, all electric charge is accumulated on the surface, and electric field exists only at the surface and outside conductor. However, when we have electric current, we are operating under conditions which are out of equilibrium. And of course, the driving force, there should be some reason why charges are moving in some direction. And the driving force for this is internal electric field. So it exists inside the conductor. Also, we considered in details the microscopic nature of electrical conductivity for like ohmic conductivity. Means ohmic conductivity, it's conductivity which follows Ohm's, like obeys Ohm's law. It's not universal law. It works only for certain types of conductors. For instance, for most metals, Ohm's law works, and for most pristine materials which do not have any non-uniformities of electric field inside themselves, Ohm's law is working, and we consider the microscopic nature of this Ohm's electrical conductivity, assuming that we have charge carriers which gain kinetic energy while moving between two successive collisions with crystalline lattice of the material. And once they, so it defines this time between two successive collisions is defined as time of free flow of light of charge carriers. And once they interact with the atom of crystalline lattice, all gain energy, kinetic energy, which charge carriers gain because of electric force exerted on them. They just transfer it to crystalline lattice. So this crystalline lattice starts to oscillate more, and temperature increases. So definitely at this point, you feel already that electric current transforms some energy. So it's like transformation of electric energy into internal energy, into heat, and it can transport energy. This electric energy can be transported with electric current via wires. And our today's topic is in particular understand the electric power, what it is, and give a clear definition and quantify this concept of electric, of the property of electric current. Okay, so now we change the screen and let us consider first such simple electrical circuit when we have a battery and some resistor connected to this battery. So here we have plus, minus terminals of the battery. Let's consider some point A, point B, point C and D. So let's assume that we have some charge transport, like positive charge transport, which means electric current in the like clockwise direction. Because we remember that the direction of electric current is defined by the drift velocity. It's velocity in the direction of internal electric field with charge carriers gain because of electric force. So if we have positive charges with certain drift velocity, the direction of drift velocity will be the same as direction of electric current. So let's assume that we have some positive charge Q, which moves, like starts to move from this point A. So once it moves from point A to point B, there is certain potential difference between the terminals of the battery. And that means that battery does some work on this electric charge. And this work is done by transforming its chemical energy. Usually we have some chemical sources of chemical power sources, which are batteries. So there is a transformation of chemical energy to electric energy. And this energy can be quantified as, let's say, change in potential energy of electric field here will be Q times delta V. So we have certain potential difference between two terminals of this battery. Then we have charge transport between point C and D. So once this charge Q is moving through resistor R between points C and D, and also we assume that connecting wires do not possess any resistance. So they kind of ideally conductive. So once charge Q moves through points C and D, this gained electric energy will be dissipated because there will be certain resistance for this charge to move through the matter of this resistor R. And because of collisions with the crystalline lattice of this matter, this gained electric energy from the power source will be dissipated. So it will be dissipated as in the form of heat, because of each of these collision of moving electric charge will cause increase in oscillations of the atoms in the crystalline lattice, and these oscillations of the crystalline lattice, it's proportional, directly proportional to the temperature of the crystalline lattice, and that's why by increasing these oscillations, we will increase temperature of this resistor. So that means because of, depends in which environment this resistor is located, it will be certain dissipation of energy by convection, or and also by irradiation, because we can, like bodies can lose their internal energy via radiation too. If it's vacuum, then it will be only loss of internal energy wear radiation. And let's a bit consider one example why it is important to take into account this fact that electric energy is dissipating on resistors. So this resistor could be called as some load resistance. Load means like very general statement because it could be just a resistive element or just some piece of wire, or it could be some sophisticated electrical device. It doesn't matter because it just considered as some load for the battery because it has to provide, convert its chemical energy to provide enough electrical energy to run this device. So let's take an example, some CPU of a computer, like some laptop. If you open or your desktop, you can see on the motherboard some square, which is covered with quite sophisticated nowadays cooling system with some heatsink and fan. It could be some active heatsink with thermal pump, so which combines thermal conductivity and thermal and convection effects in order to enhance heat transfer from this processor. So processor is a very complicated device which contains a lot of elements. However, the building block of this, so the basement of this processor is a silicon crystal, a single crystal. And silicon single crystal is quite robust material. It can be heated to quite high temperatures without any damage. So the question is, why do you think that working temperature of processor could be like has to be not higher usually than 90 degrees Celsius? So usually you can check concentrate like this temperature of your processor with different apps, and it's something like between 70 and 90 degrees Celsius. 90 degrees Celsius is really not high temperature, so it can be hot for our perception. We cannot put our like hand on such surface. However, in terms of single crystal silicon, it's really not high temperature, and it can withstand temperatures much higher than 90 degrees, like hundreds degrees of Celsius would be still okay. For crystal, it would not be burned or damaged physically. However, a lot of efforts are put in order to keep this temperature low. And in order to explain the main reason behind this, I would like to show you like again this GV curve, so-called current voltage characteristic of a semiconductor diode. It's so-called PN junction, and it's a contact between two semiconductors, N and P-type semiconductor. So this is a building block of all electronics, and it's all the matter how small you make this PN junction, but these PN junctions, it's really the key building block of all electronics we are using. And the key characteristic of such a diode is asymmetric conductivity. So when we apply some reverse bias, like negative bias, so here's current, here's voltage. Current is almost constant and very, very small. So we can claim that this device is closed. However, when we provide some forward bias to this diode, at very low voltage, it starts increasing exponentially. So it increases very rapidly. And we can claim that this diode is open. based on this principle, we can build some logical electric circuits and implement them in microprocessor circuits and perform some calculations and stuff like that. So of course, it's kind of more on the simplified level. But the key moment here that we technically can realize is asymmetric conductivity and for different polarities of voltage which we apply to this device. So this would be something like 20 degrees Celsius. This JV characteristic, current voltage characteristic, will look like this. However, if we go to with the same device, the same dial, we'll go to something, let's say, more than 150 degrees Celsius. Crystal, the material this device is made of, will be totally fine. It's not a critical temperature, so it will not be irreversibly damaged. Nothing really will happen with the material, with the device itself. However, based on the principles how this material and device operate, we will get something like this. So we will lose this asymmetric conductivity, and it will be, this diode will operate as a simple resistor. If we lose asymmetric conductivity, if current at reverse and forward bias is the same in the through the diode, then we lose the logic which can help us to do certain calculations. So we cannot claim that this is 0 or this is 1. We have the same conditions here and here. And that's why without physical damaging of the processor, for instance, it cannot operate, and it slows down, and at some point it just stops functioning at relatively low temperatures. That's why taking into account this fact of dissipating heat, like dissipating electric energy on resistance, should be taken into account very seriously, and in particular for like CPUs, a lot of efforts are put to dissipate this excessive dissipated electric energy, like this heat, as efficiently as possible, in order to keep the level of functionality of this device at the highest efficiency. Okay, so this is some qualitative description of this transfer of electric energy and its dissipation on resistance. And now let us come to the point when we do some quantitative calculations. So let us calculate the rate of electric energy decrease, like dissipation, as electric charges are moving through the resistor. So as some current is flowing through the resistor. So in this case, we know that we have some change in energy, so we can take the derivative. And now, since we are considering the rate, so rate, it's change of energy per time. So we take the derivative of this energy change per time. And that will be equal to dQ times delta V over dt. So here, this delta V is kind of a constant parameter in time. It doesn't change. It's provided by the battery. And that's why we can write dQ over dt times dV. And this we already know from previous lecture, and I remind you in the beginning that this derivative is actually the rate of electric charge passing cross section of the conductor, and this is our current. So it's current times delta V. So this is the energy per unit time. So it's actually power, energy per unit time, which is provided by this battery to the electric circuit. And since we don't have any losses on our wires, and we have steady state conditions, means that this electric current I is not changing over time. We have stable steady state condition. It means that the energy which is provided by the battery is dissipated on the resistor. So we need to have this balance in energy transfer. And we know that the voltage drop over resistor, in this case, it will be current times R, the resistance of this resistor. And that's why the power which is delivered to the resistor and dissipates on it will be equal. So it will be equal I times delta V, because it's the same as energy provided by the battery. But now, instead of delta V, we can substitute this product. So it will be I squared times R. Or from the Ohm's law, we know that electric current can be represented as voltage divided by like potential difference divided by resistance. And by substituting now current here with this expression, we can write that as delta V squared divided by R. So this is the expression for the electric power, which dissipates on a resistor R when electric current I is flowing through it. So let us write it down again here. Will be the most important and equation here is I squared times R. So we see that the amount of energy per second, like power, which dissipates on the resistor is defined by current, and this current is in second power. So it has the very strongly defines the energy per second, which is dissipated in form of heat on this resistor. And if we want to reduce amount of heat which is generated over this resistor, then we need definitely to reduce current, because we can reduce resistance. However, it doesn't have such strong effect because it linear dependence, and here we have square dependence. So reducing current will have a dramatic reduction in the electric power dissipation on this resistor. Plus, resistance could be considered as some constant parameter because we have certain device, we cannot change it, but we can change the amount of electric, the magnitude of electric current which flows through it. So now imagine that we have such a task we have some constant resistor and let's say, of electric wires. We usually make electric wires as conductive as possible, but in real world, all conductors possess certain resistance. And if wires are very long, so if we need to transmit electric energy through huge distances from the generator, from the power plant to customers, consumers of this electric energy, then we have quite long wires, and we know that resistance is equal to specific resistance times length divided by area. So we cannot make very large area of wires, and we need a huge length because the distance is very big. Rho is constant. It's a property of the material. We can use copper, which is quite conductive and relatively cheap, and that is the best industrial conductor. We cannot get anything better. Silver is a bit more conductive, but it's expensive, so we will not make huge kilometers, like hundreds of kilometers long wires from silver. So specific resistivity is constant, area is limited, it's relatively small, and length is huge. So in total, resistance will be quite large, and we will have some losses of electric energy while transmitting electric energy from the generator to the consumable, like this customer of electric, some load at large distances. So in order to reduce the amount of energy which is lost, it is necessary to reduce the current, because current is the big issue. It in square, like square dependence defines of this lost electric power along the wires. And what an idea do you guys have? What can we do in order to transfer the same amount of energy but have small current? So electric power is defined as a product of electric current and potential difference. Yes, exactly. We need to increase the voltage and keep it as high as possible. That's why the voltage which is under which this electric lines are operating, which transmit electric energy to huge distances, is really very high. Sometimes it goes beyond 500 kilovolts, and that is insanely high voltage. So, but that allows to reduce current quite a lot, and since only current in square defines the dissipation of energy on resistor, electric energy on resistor, we can save a lot of energy. Instead of heating air, it can be delivered to customers. At the same time, it should be taking into account that it's not possible to increase electric like potential difference further. We remember that because of certain curvature, we will have, like, at some points quite strong electric field, and that will cause some corona electric discharge in the air, in the atmosphere. if such electric discharges start to occur along the electric lines, that will be also a loss of electric energy, because electric energy will be used to create and initiate this electric discharge and keep it running. So at some points, some critical voltages cannot be exceeded, and there should be some compromise between the very high voltage and the current in the wires. So there is definitely some technical limit of maximum power which can be transmitted through a single this power line. So in general, we have, let's say, such a system. Let's say this is generator. It's usually up to 10 kilovolt. Then generator where a transformer which increases voltage. We will discuss transformers later, but now I just want to show you some general schematics of this system. Transformer increases voltage from 10 to, let's say, 500 kilovolts. Then it transmits this electric energy along very long wires to some other transformer which lowers the voltage, and that goes again to something 10 kilovolts. Then this transformer spreads electric wires locally closer to customers, and next to customers another lowering transformer provides this standard 220 volts, which goes to many customers. So this is very simplified but standard system for generating and transporting electric energy from power stations via high voltage electric lines to distributed customers. Okay, so now let us consider one example which takes into account, it combines this current topic of electric power with thermodynamics, which we were studying last semester. And let us consider that we have some amount of water with mass m in an insulated container, and we have some electric resistor there, so can run electric currents through this resistor, and we increased, so initial temperature, let's say, was T1, then we increase this temperature from T1 to T2 during the time interval T. So the resistance of our resistor is R. And what else do we need to know? I guess pretty much everything. Okay, so we also need to know C, the heat capacitance of water. So let us repeat now with all this set of parameters. What do we have? We have water with some mass m in isolated container at temperature T1. Then we start to run some electric current through resistor R, and during time delta T, we increase temperature of water in this isolated container which we don't take into consideration in terms of heat capacitance, up to temperature T2. So now the question will be what potential difference should be provided to this resistor in order to realize this experiment, which is described. So let's write potential, the electric power, which is dissipated on this resistor, will be I squared times R. And that is delta V squared divided by R. So now we need to define from other side how much, what will be the power of heating the water. And since we don't have any loss, all this power of dissipated at the resistor will be transferred to heat the water in the isolated container. So we also neglect with the mass of this resistor. Assume that it's very small wire in comparison to the amount of water which we have there. So in this case, what energy should be transferred to water in order to increase its temperature with a mass of m, in order to increase its temperature from T1 to T2. This is m times C, which is heat capacitance, T2 minus T1. And since we operate with power, we need to divide it by delta T. So we now have such an equation which equates electric power dissipated at resistor R and the power of heating the power is equal to the amount of heat which is necessary to warm up water divided by time interval delta T. So from here we can calculate this voltage which is necessary, like potential difference, to realize this experiment, which will be mCR T2 minus T1 divided by delta T. Okay, so this is our answer. And now I would like to make a short summary of our today's lesson. So we discussed the fact of transferring electric energy through electric circuit. So where do we get this energy? We have battery, which converts its internal chemical energy into electric energy. And then we have dissipation. We transfer it through wires, and then it dissipates on the load resistor. So load resistor can be anything. It could be just a piece of wire, or can be some sophisticated and complicated electrical equipment. Doesn't matter. It will be always considered as load for the battery. And then we introduce quantitatively the amount, like the electric power, which is equal to the product of square of electric current to resistance R. So we see that the amount of electric power which is transferred from battery to the resistor and dissipates on resistor in form of heat is proportional to I squared. And that is the key factor which should be taken into account when there are requirements to reduce losses of electric energy in these electric circuits. So that electric current should be reduced. Okay, I believe that this is pretty much everything what we had to discuss during this lecture. Do you have any questions, guys? You're welcome. And on Wednesday, we will proceed further and we will discuss, we will start introducing the concepts of DC current circuits. So DC is direct current circuits, and introduce Ohm's law for the DC current circuits, where we will consider the electromotive force of battery, its internal resistance, because any battery is made for some material which possess certain resistance for electric charge transfer. And that's why, nevertheless, made a lot of efforts to make electric batteries with minimum internal resistance. All of them possess some internal resistance, and that internal resistance should be taken into account when we calculate electric current, like DC electric current in electric circuits. So that what is going to be discussed next lecture, which will be on Wednesday. So if no one has questions, then thank you very much for attention.
Thank you.
And see you on Wednesday. Take care. Bye-bye.
Goodbye.